Dear students, today we will discuss about very important topics in organometallic chemistry. That too, the bonding in transition metal carbon pi complexes. In connection to this, we will discuss about bonding in olefinic bonded complexes, acetylenic complexes, allylic complexes, butadiene and cyclobutadiene complexes, and pentadienyl complexes, and benzene altogether Harine complexes like benzene, cycloheptatriene and cyclooctatriene complexes. First of all, what is organometallic compound? The compound formed between organic and inorganic compounds containing direct metal carbon bond is called organometallic compound. In these metal complexes, at least one carbon metal bond should be there. Okay. In general, we can define in broader fashion like organometallic complexes are strictly formed between organic and metal complexes, metal and softer ligands like form from phosphine ligand or sulfur ligands. In connection to this, important term in organometallic chemistry is hapticity. What is hapticity? Hapticity is defined as number of atoms through which the bonded ligand attached to the metal is called hapticity. In particularly in this first structure, the oxygen molecule attached to metal through only one oxygen atom. That's why the hapticity of oxygen molecule in first figure is 1. That is, hapticity is 1. In the second complex, the oxygen molecule bind to the metal using both the oxygen atom. That's why the oxygen in that case the hapticity of the oxygen molecule is 2. That is, hapticity is 2. In third case, the benzene molecule attached to metal through all the 6 carbon atoms. That's why hapticity of benzene in that complex is 6. Next, these are the examples of organometallic complex. In the upper case, the metal in upper complexes contains direct complex are formed between direct metal and carbon organic molecules. That is, in those complexes bond is there, the carbon metal bond is there, but in the lower cases complex there is no such carbon metal and carbon bonds, but in those cases the metal is attached to either hydrogen or phosphine group or sulfur or nitrogen. Although we can include these complexes as organometallic complexes. Now, brief history about organometallic chemistry. Organometallic chemistry has really been around for millions of years. For example, vitamin B12 is an organometallic compound. In that complex, the direct bond is there between carbon and metal cobalt. Okay. Now, way back to 1827, GC synthesized the beautiful complex that is named as GC salt. Next, after that, in 1890, the nickel carbonyl complex was prepared. In 1900, Grignard reagents are prepared. In 1951, ferrocene complexes are discovered. Okay, these are the Nobel winners of in the field of organometallic chemistry. Okay, in all these complexes, the structure, the bonding is there is same bonding feature is there. That is, initially when metal center comes towards the ligand center, the pi electrons, loosely bonded pi electrons move towards metal. Then later, your ligand receives electron density from metal, forms pi bond. This altogether is a synergic effect. Okay, now we will discuss about alkene complexes. In alkene complex, first olefin forms complex with metal center through donation of pi electrons. Then later your metal center, around metal center electron density increases. Later those electrons excess electrons move towards the alkene moiety. Those electrons not going to bonding orbital. Instead of that, the electrons going to antibonding orbital of olefin. That's why the bonding between this type of bond is called synergic bonding. The whole effect is called synergic effect. Because of this, the bond order of olefin decreases and electrophilicity increases. So initially, all olefin ligands is a nucleophile. After formation of bond with metal, the chemical nature of that olefin reverses. This effect is called Hampalong. Okay. Suppose if metal center, if it is there in highly oxidized state, the pi electron density from towards ligand will be less, so that the bond order still it retains 2. Suppose the metals they are in low oxidation state, those metal centers gives more electron density towards olefin. That's why bond order decreases to 1. Initially, the bond order between olefins in free ligands is 2. After formation of bond with metal, the bond order decreases to 1. Now, similar to olefin complex, alkyne also forms complex with metal. In this case, the alkynes are more electronegative than olefin. The only difference between olefin and alkyne is the electron density received by alkyne is more compared to olefin. In this case, there are two pi bonds are there. That's why the bonding in alkyne complex is very difficult to explain, because those two pi bonds are perpendicular to each other. That's why initially, if suppose one pi bond forms complex with metal, then later second pi bond it forms complex with in other direction. That's why the bonding in alkyne is very complex. So like olefin, your alkyne ligand also gives pi electron towards the metal, then later it uses more electron density from metal. That's why the bond order reduces more effectively compared to olefin. Now we will move on to, these are the some examples of metal alkyne complexes. Now we will move on to Hlne complexes. Okay, like previous two cases, your allyl ligand also forms pi complex with many metal center. It can form either way, like by giving 1 electrons to the metal, or by giving 3 electrons to the metal. Suppose if it is giving 1 electrons to the metal, it can such type of complex are called Hlne complexes. Suppose all three ligands, all 3 carbon atoms, or all 3 electrons are involving, such type of complex are Hlne 3 complexes. Okay, now you move on to butadiene complex and cyclobutadiene complexes. Okay, like previous cases, butadiene and cyclobutadiene also forms complex with many metal center. In butadiene, there are 2 pi bonds. Either your butadiene can form bond with metal either through one pi bond or using both the pi bonds. Okay, suppose in general, butadiene ligand forms cis-side conformation complexes. Now, move on to cyclobutadiene complexes. In cyclobutadiene, as such is anti-aromatic. So after binding to metal center, it becomes aromatic because it receives electron density from metal center. That's why it gains aromaticity. Along with that gaining electron density, it will become stable. Okay, now we move on to cyclobutadiene complexes. So in cyclobutadiene is non-aromatic. Okay, cyclobutadienyl anion is aromatic. Okay, where after formation of compound with metal, your cyclobutadiene gains aromaticity. That's through that it gains aromaticity and gets stability. That's why like previous cases, this also forms many complexes with metal center. For example, ferrocene. Now you move on to Harine complexes. Like previous cases, many aromatic compound forms complexes with metal center. Say for example, benzene can form Hlne 2 complex, Hlne 4 or Hlne 6 complex by donating 2, 4, 6 electrons. Like benzene, cyclobutadiene or tropylium cation also forms complex forms organometallic compound. Like previous cases, cyclobutadiene also forms cyclobutadiene anion forms organometallic complex with many metals. With this, I will end. Thank you.